Our last speaker this afternoon is Dirk Blömker from Augsburg, and there's a title on a model from amorphous surface growth. Dirk.
Oh yeah, thank you very much, and thank you very much to the organizers for the invitation to this really nice conference, which I'm enjoying very much. So the idea of this talk is, it's late in the evening, just to give you basically a model from amorphous surface growth, which I've been working on in recent years, and well, with several co-authors, Martin Reiple, Guck, Martin Heira, Franco Flandoli, Marco Romito, and basically tell you all what I know about this equation without many of the proofs. Well, actually it's not that much I know. Okay, let's see. Okay, so it's a model which arrives in the growth of surfaces via epitaxy. So you grow a surface, or via sputtering when you try to erase a surface. It's a kind of generic model that pops up frequently in many experiments, in many models. So first we'll tell you what the model is. I have a brief summary on numerical simulations just to give you a flavor. What is the dynamics, the typical dynamics of this equation, so what's actually doing. Then I'll tell about the existence of global and the uniqueness of local solutions, which is the main problem of this equation. Then depending on how much time I will have, how much time I'll spend on the other part, I will tell a little bit on long-time behavior and the search for blow-up and singularities, which we have been tried to do recently. And the key problem with this equation is, it's a scalar equation. It's one-dimensional domain, but has problems very similar to 3D Navier-Stokes. So we have no idea how to get uniqueness of global solutions for any initial conditions. So we only get uniqueness for smooth local solutions or solutions which are sufficiently small data, something like that. So it's very similar to 3D Navier-Stokes in that sense. Okay, this is the model, and I'll probably keep it somewhere for reference. So h is the height profile. The time derivative of the height profile is given by a fourth order operator, an unstable second order part, and a nonlinearity, which causes all the trouble. So it's the square of the derivative, and then you take the Laplacian, so the second derivative. And then you add noise. The noise is usually space-time wide noise. So h is the height profile. For simplicity, well, if you grow this surface, you don't really know what happened at the boundary. You assume periodic boundary conditions on a given interval, although the surface will be much larger. And you always go to a moving frame. So it's a growing surface, but it grows with some constant speed. So you always assume that after going to a moving frame, that your average is always 0. So you just stick. So 0 is always where the surface is. And if it grows, well, you just move the 0 upwards. Okay, I will tell later what the noise is, space-time wide noise. So this is roughly the model. We only did it one-dimensional. The real-world model would be two-dimensional base space. Then you have a three-dimensional surface. Okay, what is the typical dynamics if you put this thing on a computer? If you have large domain. Oh, by the way, what I didn't tell you, all these coefficients, usually you have coefficients here. So all these coefficients are rescaled and put into one parameter, which is the length of the domain. So you can always rescale that. So that you have some dimensionless quantities. Okay, so first you have a linear instability. So if you forget about the noise, if you forget about the nonlinearity, then you have a stable operator, you have an unstable operator. That should give you linear instability. And it does what it should do. You get a characteristic pattern, well, sine or cosine-like type pattern, which is slightly perturbed, and then starts growing. Then you see the formation of parabola-shaped hills. That's the effect of the nonlinearity. So these corners are not really sharp. I mean, they're round. It's a nice parabolic equation. They look very sharp. And then it really looks like a parabola, all these hills. And then, well, it behaves nicely like any other, it's like Hahn-Hilliard equation, or it just, you have coarsening effect now. So the hills just disappear. The smaller hills are just covered by the larger hills. And that keeps on going and going until if you look long enough at the equation, or if you let your computer run for a long time, you have only one hill in the end. So this is what it does.
That's without noise.
It doesn't matter. Small noise, if you do small noise, then it looks the same roughly. Doesn't really change.
Wouldn't you expect the noise to make it nucleate new?
Well, if you make the domain large enough, yes.
It drifts, right? It drifts.
Sorry?
Oh, you have a hint. You
You have a pin, yes.
You have a hint, right?
You have space-time white noise. Usually the average fluctuates with Brownian motion, but you just pin it. You always take the zero mode out. Well, you would expect if you wait for really long enough time, then, and your noise is not that small, then you would expect nucleation, some kind of effects, yes. That hills again split or something. Or that on top of the hills you get new hills. But they're usually covered by the other hills then, very fast. Well, it's hard if you have a top of a hill to nucleate another small hill, and usually that's just by coarsening covered by the other hill. So that's the problem. Okay, so that's what it looks like. And it behaves like a nice gradient flow. Well, you have phase separation, you have something like stationary solutions, and then they coarsen, you go from one stationary solution to the other. So it really looks like a nice gradient flow. Although it isn't, and you don't have an energy or something like that. Okay, this is really numerical data done by Martin Reible years ago, and with real-world coefficients, so that's why I don't really label the scale. So he added coefficients to fit it to a model that they were actually doing experiments with, and then he calculated he calculated the surfaces. And what you see always, it's not that good, what you see always three consecutive time plots after some time. So you see this spinodal this decomposition process. Then you see this getting steeper. Then it's growing. The scale is growing, and you also see the coarsening. For instance, here you have a small hill. You have a small hill. It gets smaller because it's not growing that fast, and then at some point it just disappears. This is the third snapshot. Well, you see it all over the place. Here hills disappear. Here one is disappearing. Also, if you look at this one, you could see hills disappearing. Well, in the end, you just end up with one huge hill. So this is the numerical data in one dimension. And this is what the experiments look like. So if you do experiments and you take out the surface, so this was it's called zirconium aluminium copper. That's right. Well, this is the formula for that. It's a kind of ceramic glass. So it's not a crystal, it's an amorphous surface. And what you see in the beginning is you see some kind of hills like, if you look closer, you could see like snake-like structures where you have lines of small hills. Then if you wait longer, you get nice separated hills, where you have really blobs of hills. Okay. And one problem with these experiments is, well, you cannot just look at the experiment. I mean, the length scale is 40 nanometers here, so you cannot really look at it. And if you want to really make an observation, you have to take it out of the growth process, put it in X-ray, what is it called? Scanning tunneling microscope. You can get a picture of the surface, but you stop the growth process. You cannot put it back. So you just can take it out, have a look what it looks like, and then you can throw it away. It's not the same experiment anymore. So you can get a lot of pictures and numerical data, but always at one time shot for a different realization. So that's one of the problems if you really want to make an observation of this. I'll probably come back to that later. Okay, so you can really see that it behaves, that it has this nice structure, linear instability, growing of hills. Well, if you wait long enough, usually well, if you have enough money and you can grow the wave really thick, then you would even see coarsening here. But that takes a lot of time. Okay, what can you prove for this equation? So one very simple result, which I will not spend much time on, is this growth of hill. So when the length is sufficiently large of the underlying domain, that means that your linear operator is sufficiently unstable, then you get patterns, then hills, patterns of characteristic size of order 1, which is exactly the wave number of the dominant eigenfunction. And this is what you would see with high probability. And you can prove it actually rigorous, which we've done it for a Cahn-Hilliard equation. We haven't really looked at it in full detail to this surface growth equation, but the method should carry through. And you see this typical snake-like pattern with of a characteristic width, and you have to imagine on each where it's a little bit thicker, you have a small hill on top of it. So that's just, and the pattern is just caused by the most unstable eigenfunctions of linearization. So that's what you would expect, and that's what you can actually prove in the end. And a nice side remark is a result by Thomas Wanner. Actually, in these numerical experiments, you see that the stochastic equation has an advantage over the deterministic equation. So the good thing is, for the stochastic equation, you have a decrease of complexity of the pattern all the way over time. So it's really, the complexity of the pattern is going down. For the deterministic equation, that's not true. You have after the decomposition phase, before you get into coarsening, you have a slight increase of complexity. So that's good news. The stochastic model in that case, it's much nicer because it does what it should do. It decreases the complexity. Okay, just a remark. So that's what you could prove rigorously, but that was not part of the talk. Okay, so why I got interested in that model? So I was talking to physicists at that time, and what their problem was a kind of model parameter estimation for the model. So that was a problem, and we could work on that. So their problem was that they only get statistical data, because you can only get one snapshot of the solution every time you do the experiment. And the whole derivation of the model is really like, they have a lot of rules of thumb in that involved. Symmetry arguments that cancel out terms, and so there's no really rigorous derivation from molecular dynamics or something like that. It's more or less like symmetry arguments, rule of thumbs, geometric arguments based on curvature, then brute force linearization, all these kinds of arguments. So in the end, they don't know what the coefficients really of the model are. So what kind of coefficients to put here? And there, what they implemented was just a brute force estimation via Monte Carlo simulation, and then optimizing by hand. So they were just putting in some coefficients, let it run 100,000 times overnight, look back what the numerical data looks like, average some statistical quantities, try to match it to the experiment. Doesn't work? Okay, you take another set of parameters. And so they really fitted the model to the equation, the equation to the model in the end. Okay, so that was what they're doing. What they were actually approximating was statistical quantities, for example, the mean surface width, or what they call it roughness, which is the variance, the spatial variance of the height, and then averaged over space and probability. So you have the height minus the spatial average, you square it, you take expectation, you average with respect to x, to the space. Well, but if you assume that you're in a moving frame, this term is gone. What you actually compute is just the expected value of the L2 norm squared. So it's a very simple quantity. This is what they actually compute. And this is something they could measure. This roughness is something they could really measure. Because the other problem is if they do the experiment, all these wavers, if they're growing, are rotating, and they're not really knowing where x and t is if they take it out of the process. So that's why they only know from experiments average quantities. Okay. And then the task was to calculate them. Okay. So for nonlinear SPDEs, the numerical simulation is not really well known, especially at the time that we're looking at these equations. And there are quite a few worked in recent years. Well, you just heard one talk. And what he did at that time was just spectral Galerkin method. Actually, the physicist first implemented finite differences with tiny little spatial discretization. Then they just bought a few new computers to make it run. And what you see from the numerics, the equation is really nice and well behaved. It converges very fast. So I didn't give you the numbers, I just plotted a picture. So for n, we had 2n plus 1 modes. So this is about 50 modes, well, 40, 50. And then in the end, we went up to, well, about 200 modes. And it converged very fast. So you can really estimate a posteriori numerical error. And, well, they all coincide more or less, all these numerical approximations. And why they deviate in the beginning, well, you have not enough modes to resolve the stabilization effect. You just see that the linear instability takes over the nonlinearity. You're not having enough modes to get stabilization due to the nonlinear effects. That's all. But if you get that right, it works perfectly. Okay, so it looks very good. So we thought, well, we just prove existence, uniqueness should be standard, and then we go to the interesting problem. And we got stuck by proving the existence and uniqueness. Okay, let me give you the key and the only point, the key estimate for existence of solution. You need an a priori estimate to make any approximation procedure run to get it to converge to a solution. And well, the only a priori estimate we know is the standard one. There's no other one known. So the only thing you can rely on is, well, you multiply with h, integrate by parts, then you get nice a priori estimates, and then you can try to prove that the spectral Galerkin method converges. Okay. So let me show you the estimate just for the deterministic example, and without the linear. The linear part, the second derivative doesn't change anything. It's just lower order term. It just mixes up the estimates, and the same with stochastics. You can do it for the SPDE also. You just have the stochastic convolution somewhere inside. It just makes the estimates more complicated. But the key problems are these terms. This is the best one. This is the worst one. So the idea is you multiply by h, integrate by parts, and then the nice trick is you have periodic boundary conditions. So once you have a primitive, the term is 0. It disappears. Like in Navier-Stokes, where you have divergence-free vector fields, it's gone. So the only term that are left are the linear part and the derivative of the L2 norm. So on the left-hand side, you get the derivative of the L2 norm. On the right-hand side, you get minus the H2 norm. Well, it's minus, so you put it on the other side, you integrate, and you have the norms bounded. Okay. So you have the integral of the H2 norm squared bounded. You have the L2 norm uniformly bounded. So you have a nice a priori estimate in time, uniformly with respect to the initial condition. So this is the regularity you would expect, L infinity, L2, and L2, H2 for all times. Okay, that's it. You cannot get more. Okay, you can get more. There's another one, but which is unfortunately useless. So you can take the integrals over exponentials of h. You do the same. You try to prove a priori estimates, and you can prove that these are actually stay finite. So you know that, for instance, the positive part of the solution will be much more regular. You can integrate it in any LP. It's uniformly bounded. So it's not only L2, it's in any LP, so you have much more regularity. But the sad news is, well, it's only the positive part. And it's still not quite enough for regularity. So you're slightly below continuous, and continuous is somewhere the borderline. It's a critical space. So you need more regularity than continuous. This is below that critical space. Okay. So It's the only other a priori estimate we have, and it's unfortunately completely useless. Okay, so what's now known and what's now known for the SPDE? So the first result where we started from was, well, we could prove there exists a solution, mild martingale solution, just showing that the spectral-Galerkin method converges. This is very similar to the work by Kavinsky, Gatarek, Flandoli, Daplata, Debouche, Odasso. So we just proved that it converges. Then, well, I already showed you the result on the numerical convergence. That was mainly numerical experiments, which were working very well. Then there's the results by Martin Heira and myself. We proved basically by also exploiting convergence of the spectral Galerkin method. We took the existence of a stationary solution for that equation. So basically you take the spectral Galerkin method, you take the stationary solution of the spectral Galerkin method, and you show that they converge. Well, that's the limit will be stationary and it will be a solution. So that's the idea. And well, I just want to mention that Wilhelm Stannard has some nice improved moment estimates for this stationary solution. And he's working on trying to prove basically that, well, that you get uniqueness of the Kolmogorov operator. But okay, so if you want to know anything about Kolmogorov operators, you should probably ask him then. Okay, then some work with Marco Romito and Franco Flandoli. We actually took their result on 3D Navier-Stokes and carried over through to this equation, which was surprising because in some part it was much easier, as we would expect it. In some part it was much harder than Navier-Stokes. So I'll briefly tell you a little bit on that result. And recently, I've been working with Marco Romito, try to understand how this equation could possibly blow up or have non-uniqueness. That's just emphasis on we try to understand. Okay, so I didn't tell you up to now what the noise is. Well, we take space-time white noise. You could take any colored noise, which is nice. So any colored noise with spatially colored noise with more regularity than space-time white should be fine. You could even have something which is slightly rougher. That should work also. Okay, so this is the way you write if you're a physicist. So what you do is you have a standard cylindrical Wiener process in L2, which is just given by a Fourier series with IID Brownian motions as coefficients. And this is then your driving noise. Well, for most of the talk, I would just restrict to that case, although most of the results will hold for more regular noise, where you add coefficients here. But it's just technical details. Okay. Then I already told you that existence result based on this a priori estimate. Okay. So I didn't tell you what I mean by mild martingale solution. So the idea is, well, you fix the initial condition, you fix your time, and then for this given initial condition at the given time, there exists a probability space. On that, you have to construct a Wiener process and a stochastic process with some kind of regularity. Basically, the difference, that's exactly the regularity you get from the energy estimates, plus some continuity in time. The h minus 3 is probably by far not optimal. Okay, this refers to the martingale in the solution. That's what we call the martingale solution. And it's a mild solution because we looked at the variation of constants formula. So you look at the semigroup generated by the linear operator A with periodic boundary condition. It's just your fourth order and your second order differential operator. But then you write down the standard mild formulation, the convolution with the nonlinearity, and the convolution with the noise, which is a stochastic convolution. So you just try to solve that equation. And in that case, it's nice because you have a fourth order equation. If you have space-time white noise, you know that your stochastic convolution is actually a Hölder continuous, only wrote continuous, but it's Hölder continuous. And the derivative, the spatial derivative of the stochastic convolution is also Hölder continuous. So the stochastic convolution is really a nice function. It has derivatives in space and it's Hölder continuous. Okay. What's now the idea of proof? As you know that you have a derivative of the stochastic convolution, you can just do the standard trick. You define a new, you make a change of variable, you subtract the stochastic convolution from your height profile, then this difference solves the random PDE, where basically you get rid of the noise and you have it as an Ornstein-Uhlenbeck in your nonlinearity. So that's the standard trick we've seen several times during the conference. And now you can do basically the energy estimates that I showed you for the deterministic equation. You can multiply with V. You do all this integration by parts, cancellation of the cubic term in V. You have some term where the stochastic convolution is involved, but you get basically the energy estimates, where the bound, well, depends on the Ornstein-Uhlenbeck process. And then you use compactness to pass to the limit in the standard way. You show the tightness of the laws for the spectral-Galerkin approximation, and then you use the theorems of Prokhorov and Skowheroth to change the probability space and actually get a convergent subsequence, not only as measures but really pointwise as functions. And then you can pass to the limit and the equation, and you know that you have a solution. So that's the very brief outline of the talk. It's fairly standard. Okay, so that's the global existence of solution for any given time for L2 initial data. For the local existence, we did fixed point arguments, as you would expect. And the result that I present here is a result that's based on the old work by Fujita and Kato, which we've already seen in another talk by Kim. And there's some other works in the same direction, but this is the result with Marco. So you have given now the noise. And then if you take initial condition, which are h a half, so half a derivative is L2, then there's a stopping time or a local solution such that the mild formulation has a unique solution which is given as a fixed point in that space. So you have a weighted space, a space weighted in an L-infinity space in time, which is weighted with a pole at 0. And you have the h to the 5/4. So what you take here is not really important. It can be anything between 1 and 5/4. We took 5/4. It's not really important. So this 5/4 is flexible. Okay, so you know that this norm is finite. And you also can prove if this norm is finite, then the solution you constructed is actually as a fixed point in that space. You use the mild formulation, you can actually show that it's really continuous into 0. So the initial condition is really attained. Okay. And you can show that the solution H is smooth between 0 and tau star. And what do I mean by smooth? It's as smooth as a stochastic convolution. So the difference is much more regular, and then H, the surface, is as smooth as the stochastic convolution. If you have a smooth stochastic convolution, then the solution H is smooth. If it's space-time wide noise, you would expect that H is actually continuous, Hölder continuous in time, and C1 in space. But it might blow up. Maybe, okay. So I will not give you the details. So the details are fixed point arguments, and you have to work a long way to just make this method work. Just 2 comments on that. So actually you do not need h a half. So you can be slightly more general. What you actually need is some kind, what they always call the caloric extension, has to be in that weighted space. So if you apply the semigroup to this condition, you have to be in that space, and it has to go to 0 if you send t to 0. So that's slightly more general than h a half. Not really much, but it's slightly more general. And it's not really necessary to work in h a half. So you can make this argument work in a lot of type of spaces. So we stick with Hilbert space setting for simplicity, because it was just using the very much along the line of Fujita and Kato. But you can also work with BMO type spaces, or not quite sure about C0, that's work in progress. But in principle, you can make this argument work for a whole scale of spaces like W alpha P spaces or something like that. The largest space would be some kind of BMO type space. And then you can follow the work of Koch and Tataru. And the most general norm you could use is this weighted C1 norm. That would give you some kind of BMO type spaces, as Koch Tataru were using in their work. And they always claim that's the largest possible space if you want to have a weak solution when you integrate against test functions. So it's exactly, these spaces are exactly the spaces that you which of regularity that you need to make sense out of the weak solution when you integrate the PDE against the test function. So. Okay, but this is H1/2. This is C0. Even these BMO type spaces will be only slightly better than C0. So you're not getting below that threshold with local existence. But you still have a gap. The global existence is L2. You have a quite wide gap. So the energy estimates provide you only an L2 bound for H. So the L2 norm is bounded, but it doesn't help you because the H1/2 norm might just blow up, or the L infinity norm. So we have this gap of regularity as in 3D Navier-Stokes. Okay. Whoops. Okay, that's somehow first the bad news, that it doesn't work that easy. The good news is we now have another equation where you can use all your machinery for Navier-Stokes and test it. And see if the machinery is only designed for Navier-Stokes or if it can give you something else, if it works only also for other equations. And it's not like an artificial example, it's really a nice PDE. And on the other hand, it's much nicer. I mean, Navier-Stokes is a system. You have a three-dimensional system, and this is just scalar. So. Okay, so what else is known? So the work with Franco and Marco, we could show that you have actually, the solution is not this martingale solution, but it's actually a family of you can actually have a nice Markov process. So you have a family of solutions that forms a nice Markov process. And the result is you can prove that there's a family of measures indexed by the initial condition in L2, which is supported on the phase space, so it's continuous, well, H-3, locally continuous. It's locally L2 in H1, so it's quite less regularity. Actually, it has later the regularity you would expect, such that you just take the canonical process, the identity on that omega, so this space here is your omega. On that you have the identity, it's a process, and you can prove that it's a weak martingale solution to your surface growth equation. And in the sense that, well, if you integrate the equation, throw everything to one side, so basically integrate whatever you have here, bring it to one side, solve for the noise, then the thing that you already know is the H. H is just the identity. And then what this term here should give you the Wiener process. So it's a weak martingale solution in the sense that this one is exactly the Wiener process you would like to have. And what you need for the solution is you cannot prove it for any. You need some kind of, you need the energy estimates. That's what you have to plug into the concept of solution. But V is now H minus the stochastic convolution. Well, we have the Wiener process. You can define now the stochastic convolution. And this V should satisfy the energy inequalities. I didn't write them down, they're quite long. But it's exactly the energy inequalities you would get if you do the formal calculation. So that's what you put into the equation. And then you get that V is actually, your V is actually satisfies the energy regularity, and it's now a global solution. And the key point in that approach is it's not really a Markov process. So H of t is no Markov process on the same probability space. And there's no approximation used. And the key idea is this abstract method of Markov selection. It goes back to the work of Franco and Marco for 3D Navier-Stokes, and recently Ragnar, Goldis, and Sang used a similar approach. Okay. And then if you have a Markov process, you can talk about long time behavior. So what I knew from the work with Martin, that we have a stationary solution on some probability space somewhere around. Now we have a Markov process, and then the other half of the work with Marco and Franco was to show that actually each of these Markov processes has its own unique invariant measure. So for simplicity, forget about the nonlinear stability. Assume that there's no linear instability. So just forget about this term. It works exactly the same way if you have this term inside, but the estimates are much more involved in that case. You need to have gauge functions and all that stuff. So just forget about the linear instability. And suppose that the noise is sufficiently rough, so space-time white noise is good. Then you can prove that every Markov selection actually has its unique invariant measure. And the idea of proof, well, it's Dup's theorem, and the most of the work was done to prove actually strong Feller. I mean, it's space-time white noise, so the other parts are fairly easy. The hard work was done in the strong Feller, which we done by Bismuth-Elworthy-Lee formula. Well, then it doesn't really work. I mean, you have a non-unique solution, so you cannot really apply this. So what we have to do is you have to look at a regularized problem where you use some kind of cutoff, where you cut off the nonlinearity. Then you know up to some stopping time, the regularized problem where you just cut off the nonlinearity coincides with the actual solution that you have. So all the solutions are the same after that stopping time. And then you have to, for this equation, you have no problem applying Bismuth-Elworthy-Lee formula. You can do all these estimates, apply all the machinery, and then you have to somehow carry that through by controlling the stopping time to the Markov selection that you have, to the Markov process you have. So that's the key idea. I'm very summarizing 20 pages in just 3 lines. And at that time, the unexpected thing was that the existence of an invariant measure was hard. So we had no uniform bounds at that time on moments of solutions. I think the work of Wilhelm would solve this. So the hard part here was actually the existence of an invariant measure via this Krylov-Bogoliubov method. So we had to work a long time, so we were not able to prove logarithmic moments or even double logarithmic moments. Okay. So that was the key problem in that, which was surprised us somehow. And why one is doing all this? I mean, the key goal is, in the end, to prove your uniqueness of the weak uniqueness of the solution. And there's one result that tells you, well, if the invariant measures you get, all of them are unique for the given Markov selection, but if all of them are the same, then the whole problem is well posed. But it tells you that the problem is not that easy to show that all these invariant measures are actually the same. You have some relation between the different Markov selections, but it's quite a hard problem, but that would be a final goal in that direction, to prove that it's really well posed. Okay, so we have this gap of regularity, and we don't really know if there is a blow up or not, or if there's a loss of uniqueness. So what we tried recently was to understand in which way the solution could blow up, or why it shouldn't blow up. And the question is very similar, either for the PDE or for the SPDE. It's easier for the PDE, but then you can usually carry over most results to the stochastic PDE. So let me give you just first a few arguments why there might not be a blow-up. And the the standard reason, you do numerics, it works very well, so you wouldn't expect that thing to blow up. Okay, that's no proof, but if you simulate it on and on and on and it never blows up, well, or it never behaves strange, then it looks very good. There's at least hope. The other thing is, it behaves really like a nice gradient flow. So once you're in this regime, it has linear instability coarsening. So it's really a nice equation. So it seems that there's really a deterministic attractor around, which consists of stationary solutions and heteroclinics between. So it really behaves like as if this attractor would be there. So that's the argument why there should not be a blow-up. So why could there be a blow-up? I mean, there are two arguments. So one is if you look carefully at the numerical simulations, these corners are really, I mean, they're round. If you zoom in, they're still round, but they're pretty sharp. So you could think, okay, probably at some point it just makes flip and it's a straight corner. Then you lose regularity and you have loss of regularity. And you have non-uniqueness probably. That's something you could expect just from the picture. Another argument is there actually are stationary solutions that blow up. Well, they are not really stationary solutions, nor in the mild nor in the weak sense. It's just if you plug in this surface H into the equation, it's a stationary solution up to the poles. So you can just show that if you take something, a logarithm of a cosine, well, this is just a shift in phase, more or less. You can show that this thing has obviously log-like poles going to minus infinity. And it solves this equation where it solves the stationary equation without the linear instability. Forget about this one, forget about the noise, forget about the linear instability. Then you can just sit down, some basic calculus, and you can show that it solves the equation. It's a stationary solution, well, up to the poles. But you cannot show that it's a mild solution, nor you can show that it's a weak solution because of the poles. And it actually fits in any domain. If you choose your B right, then it's nice periodic and it fits into the domain. And the other thing is, what puzzled us is, they're exactly at the borderline of regularity. So the regularity threshold somehow is h1/2. Well, they're not better than h1/2. They're slightly worse. I mean, they fail to be in any hs for s bigger than a half and equal at half. So not in h1/2. Yeah, they're not in h1/2. And on the other hand, they're not in C0. They're not in this BMO type spaces. So they're just below the regularity where you can prove your global, where you can prove your where you can prove your local uniqueness, existent uniqueness result. We have no idea how to exploit that, but some of the puzzling fact that this could tell you that there really is something like a blow up. Okay, what are the partial results that we actually have, what we can really prove? Well, you can do energy estimates, you can do pathwise estimates either for the PDE or for the SPDE, and you can show that if any of the HS norm blows up for some S bigger than a half above your regularity, then it's the classical Lie type result, then you know that it has to have a sufficiently fast blow up. You can give a lower bound on the blow up. This is just based on the energy estimates. So you have this lower bound on the blow up if there is a blow up. And on the other hand, you can prove that if the HS norm blows up at some time, for some S which is above the regularity threshold, then all norms would blow up. So this would exclude, for instance, the blow up as a cast. So this one, where you have a corner here, is actually excluded. It has too much regularity. This cannot be a singularity because this one is still in h1/2. or it's even better than h1/2. And it also excludes blow up where you have a spike, where a solution looks like a spike, like a square root. This cannot happen. It doesn't have enough regularity. And you can sit down and you can do, this is just Hilbert space theory, that was more easier to prove, but you can sit down and you can prove it for other norms. You can do C0 W alpha P, which is much more work then, but you can do in principle, this result should hold for any norm where you can prove uniqueness. If it blows up, this norm would blow up at the blow up point. Okay, so what are other topics or work in progress? Some of them are done. So one thing we would like to exploit is that this blow up of H minus is more likely. So you have this strange Lyapunov functional where the integral over e to the h was bounded. So you have more regularity from the positive side, and even if you look at the solution, somehow it has more regularity here than down here. So you would hope that you can prove some criteria that the blow up to minus infinity is much more likely than to plus infinity. Then what's mostly done is extend the uniqueness result to other spaces. That's this BMO spaces or space of continuous functions. Then what you did for a long time was study, like in Navier-Stokes, study self-similar blow up. And from the scaling, you would expect it to have a self-similar blow up which is logarithmic. But you have not enough structure to actually prove that anything about self-similar blow ups. The equation you would get if you plug in the self-similar blow up, which is self-similar, into the equation, the structure you would get is exactly the same as you have, plus some extra term which makes your life even worse. So this would not really help you. And a funny result we had for the deterministic PDE, which is based somehow on Sinai and Lee for the 3D Navier-Stokes. So we have a very simple proof that for the PDE, you can find actually many complex valued solutions that do actually blow up. They have singularities, they blow up in finite time. So our proof is, well, we have a very short proof of that. And Sinai really gets the asymptotic of the blow up for 3D Navier-Stokes right. So you really can say how fast it blows up. We can just say they blow up at some point. And well, the message is now, well, if you know that they blow up you have a blow up for complex valued solution, then once you do energy estimates usually hold for complex valued or real valued solution. They will not give you any difference. Usually you take the absolute value and then it doesn't matter if it's complex or real value.
Not for Navier-Stokes.
Yeah, for my equation. Yes. For the surface growth, yeah.
For Navier-Stokes, there is no energy estimate if you take complex valued functions.
Oh yeah, you lose the energy estimate, yes. But the same here, you lose the L2 estimate. That's the thing, the L2 estimate, the energy estimate is really based on the fact that your solution is real valued.
Yes, but for if you take complex,
then you lose that, yes.
you lose, yes.
Yes. So the point is, so you lose, also in this case, you lose, for complex valued solution, this is also not true anymore. So you lose this trick to get energy estimates. So either you rely heavily on the uniform bound on the L2 norm, or if you're not relying on that, then you can do it, any energy estimate you do is basically also valid for complex valued solution, like this Leray bounds and all these estimates. Okay, and this is basically what I want to tell you. So this is all we know up to now for this on this model for surface growth. We know that it has the same problems in 3D Navier-Stokes, although it's much simpler. Well, at least it looks much simpler. We know that we have global solutions, which are Markov processes. But uniqueness of local solutions is only for much smoother initial conditions. Although numerical approximation looks very nice for this equation. Okay, you can say something about the invariant measures the long time behavior, and some results on blow up. Well, I'd like to thank you for your attention.
So I'll ask you the same question I always ask Sinai.
Okay.
So do you believe in blow up or not blow up for your equation today?
Good question. I don't think it has a blow up. I don't think so.
Well, what's the most likely shape of the candidate?
Logarithmic. A logarithmic pole.
Logarithmic fold, that's what you think it is.
And that would destroy, well, if you can prove that, then it would destroy all the work for the physicists. I mean, if you have a logarithmic blow up, you go down. So you expect something like a logarithmic pole. Well, that means at some point your surface, which is grown on a waver, goes all the way down to minus infinity through the waver. So it doesn't make any sense.
And here's the last part of my standard question.
Okay.
Do you believe that noise retards that?
Possibly, if it blows up. But it's the same as.
Have you thought about that? I mean, is there any reason?
Yeah.
Because all the stuff you said in the end about the blow up had little to do with the stochastic version.
No, it's not. It's really the blow up
It's really
pathwise determinant also for the deterministic equation.
Right.
What kind of blow
So
up
I'm
is
asking,
there?
I guess, if you thought about, do you have any feeling, I mean, it doesn't have to be a mathematical theorem. I was just curious what your opinion was.
I don't know. It appears that the blow up is fairly thin. So it's not really that the broad region blows up. So if you have noise, then probably, even if for pathwise, you will never hit this blow ups. So that's what I would believe for this equation.
So you don't think noise either blows up or doesn't, and noise won't change the answer?
Oh no, noise would change.
Oh,
change
yeah,
the
noise
answer.
would change the answer.
So that the blow up, where the blow up happens, is very thin, say very thin channel. And if you add noise, you would never follow that channel. You would just always go away. Something like that. This is what I would.
Even if the deterministic blows up, the noisy one might not.
So really, it might be just a very thin manifold that goes off to infinity. But speculation. No, not really. Don't really know.
Any more questions?
Well, in the surface growth, you work in nanoscale, for example. Especially the atoms that they fall down in sputtering, they are of nanoscale.
Mhm.
And the question is more philosophical, whether the right model to model such a behavior is this continuous equation, or if deterministic one would be better, for example. That's the question.
Sorry, what?
Have you considered like discrete model of
No.
your equation?
We just took the model that they had. So you could think of discrete models, yes, but that's something you can not really simulate. And the structures are very small, but they're still, in the Hills had length scale of a few hundred nanometers or 400 nanometers. That's still quite a lot of atoms in there. I mean, you can always argue about the model. I mean, the model, so even if you do the growing, you have these particles going down, you have the surface, and it's not that this particle is nicely going down, lying around here. What it actually does is it goes inside and it blows makes a small crater. So they're hitting the surface with velocity. So you can always argue if this is the right model. It's just a phenomenological model that should describe the behavior.
I know that there are some papers that derives similar equations from the discrete case, or if we look at some limits. So is this particular equation derived from such
No.
rules?
It's really a phenomenological model. So it's not derived from microscopic principles. The problem is really if you want to do this from microscopic, it's not really like a crystal where the surface is solid. It's very soft. You have a whole layer of atoms bouncing around back and forth. You have to get this crater if you blow in. If you really want to do particle simulation, you have a lot to do. Because the surface is not static. So I have no idea if that works.
Any more questions? Are the periodic boundary conditions also phenomenological? I mean, I didn't understand.
That's
It's easy to work with periodic boundary conditions, but
well, they don't really know what the boundary conditions are. So what they usually do is they have their waver and they look just as some small range. That's what they really look at. And then here something is happening. And here you have, well, here obviously you have boundary conditions because all the particles are falling down. But they don't really know how to describe the boundary conditions. So that's why they say, well, if you make periodic boundary condition, it's a good approximation if your domain is large enough. So that's the usual argument they have.
Physicists don't. Okay, so if there are no more questions, can we thank Dirk and Paul this afternoon?